All right, go ahead, Niklas.
Okay, welcome to my presentation on open source virtualization layer for CUDA applications. I'd first like to start with a quick motivation. While GPUs have achieved widespread adoption in fields like HPC and cloud computing, the research into otherwise commonly used virtualization techniques is hindered due to the closed source nature of the NVIDIA drivers and CUDA. So fine-grained control of the interactions between applications and devices is not possible. We therefore add a virtualization layer to CUDA applications that allows us to execute the CPU and GPU parts of CUDA applications in separate processes. This allows us to get full control of the device interactions between the CUDA applications and the devices. The previous work on virtualization for GPUs includes RCUDA, which focuses on the remote execution of CUDA applications and uses a similar server-client structure than our solution. However, RCUDA only supports CUDA 9, so no Turing generation and later GPUs, and it's not open source, so it does not allow customizations. Furthermore, there is the CUDA multiprocess service that allows multiple CUDA applications to share a single GPU, but also here there's no source code available. Then Docker also supports NVIDIA GPUs to be used inside Docker containers since version 9.03, but the CUDA applications inside the Docker containers still interact directly with the host's device drivers. So this is no proper virtualization and offers no clear isolation and separation. So none of these available solutions supports current devices and allows the customization of the code. So some applications where a virtualization layer that is customizable can be of use are shown here. In the top left, we have several CUDA applications running on different nodes in a cluster. Using the virtualization layer, it is possible to use a GPU for execution that is installed in a system that is separate from the systems where the CUDA application was originally started. So the nodes A and B here don't even need to have a GPU installed, while node C can execute the GPU-related code from these applications. On the top right, we have multiple CUDA applications sharing access to a set of GPUs, while a scheduler can control and limit the GPU resources in a customizable fashion. The bottom shows a checkpoint restart, where the execution state of CUDA application can be saved mid-execution and can then be restored at a later point, thereby increasing fault tolerance. For checkpoint restart, we need virtualization to record the device interactions during the execution, so we are able to rebuild the driver's internal state at a later point in time. Before I get into the implementation details of our virtualization layer, let's have a look at the CUDA software stack, how it is normally used in the top. CUDA applications usually use the CUDA runtime API to interact with the GPU. This runtime API itself builds on top of the CUDA driver API, which is loaded during startup using libdl. The CUDA driver API then interacts with the GPU devices and the GPU via the NVIDIA driver via some sort of inter-process communication scheme. While it would be ideal to insert a virtualization layer in this software stack as low as possible, so ideally at the driver, because the driver and all of the CUDA APIs are closed source, this is impossible. So we opted to instead insert the virtualization layer, here shown in green, at the level of the CUDA runtime API. This isolates the CUDA application from all of the proprietary code of of the CUDA APIs and driver. The virtualization layer is built using a client and a server who communicate with each other using remote procedure calls. And so the left part and the right parts are executed in separate processes. The replacement of the CUDA runtime API with our virtualization layer works like shown here. First, we built a library that exports the same function symbols as the original CUDA API library. And this library can then load instead of the CUDA library using either the LD preload environment variable or replacing the original CUDA library in the library search part of the operating system. Our replacement library then executes like a wrapper that instead of executing the original CUDA API functionalities, sends RPC requests to the server application. And in the server application, we then execute the original function, collect the results of these CUDA functions, and send them back to the client. This process of the replacement is completely transparent to the application and requires therefore no recompilation or code modifications to the CUDA application. One caveat is that the runtime API has to be linked dynamically to the CUDA application to enable the replacement. When the CUDA runtime API is linked statically, we cannot replace the library during the startup of the application. Another challenge was that the NVIDIA compiler NVCC adds some hidden CUDA initialization code to CUDA binaries that is necessary to start kernels. To be able to execute this initialization code, we also use the original binary for the RPC server application and preload a custom library that instead of executing the original CUDA application, uses a library constructor to execute the CUDA initialization code and then waits for requests from remote procedure calls. So the original main function is in the server application never executed. So we use remote procedure calls to execute functions in a different process. We use the TI RPC library to implement the remote procedure calls. This allows us to send remote procedure calls either via an IP or a domain socket. So when we want to use a GPU that is connected to the same system where we start the CUDA application, we just use a loopback device or a domain socket for this communication. And for GPUs that are installed in remote systems, we use just TCP/IP over an Ethernet connection to send the remote procedure calls. If we have a new API function for which we want to implement a remote procedure call, we just use our interface definition file where we just add the respective API. This then from this the TI RPC generator then generates client and server code that is able to execute the remote procedure calls. And if we want to then in the client application, that is basically the replacement for the original CUDA function. When we want to implement this, we just create a function that has the same prototype as the original CUDA function. And in the body of the function, we only call the remote procedure call and receive back the results and return it to the CUDA application. So adding new functionality is pretty straightforward in this with this technique. Another big point is data transfers via CUDA memcopy, while most APIs can be just done via the remote procedure call mechanism. Data transfers, we have to give a little bit more thought. So for normal CUDA memcopy operations, we need to first, before we can transfer the memory to the GPU, transfer it from the CUDA application to the RPC server. So we copy this also via a socket. And then from the RPC server, we can call the usual CUDA memcopy call and copy it to the GPU. As we can see, these are now 2 copy operations instead of only 1. So copying is definitely slower than without the virtualization layer. Fortunately, there's also the pinned memory API, where during the allocation of the memory of the host memory, we can use, instead of the libc's malloc function, we can use CUDA host alloc to allocate the host memory, and then increase the performance when we want to transfer to the GPU. With the virtualization layer, we can benefit from this API by setting up a shared memory segment between the RPC client and servers during the allocation of the memory. And then when it's time to call CUDA memcopy, we can directly copy the memory from the original CUDA application to the GPU via the shared memory segment. Of course, this is only possible for local GPU usage, but even when GPU and CUDA application reside on different nodes in a cluster, we can use InfiniBand's remote direct memory access facilities to increase the performance of these copy operations by setting up an RDMA memory segment during the memory allocation phase, and then when we call CUDA memcopy, directly copy from this remote RDMA memory to the GPU. To test our virtualization solution, we use 2 systems. First, our main evaluation system consists of 2 Intel Xeon Gold 6128s, one NVIDIA Tesla T4 and a Tesla P40. The second system was only used when we use remote execution. So the CUDA application was started on this system, and then the RPC request was sent to the other system. So the second system consists of 2 AMD EPYC 7301s and no GPUs. And both systems are interconnected using a 100 gigabit InfiniBand connection, which was either configured to use IP over IB or directly using InfiniBand. We performed a few application benchmarks measuring the performance when using a locally installed GPU and when using a remote GPU. And then also 2 micro benchmarks where we measure the latency of API calls and the memory transfer bandwidth. So first, about the application benchmarks, we used these 4 applications. The first 2 metrics, mul and nbody, are from the official CUDA SDK in the samples. The first one just performs matrix multiplications. The second one is a physics simulation. The third one, hotspot, is from the Rodinia benchmark suite and performs a thermal simulation. And the third one, dpsim, is an electrical system simulator. We measured first the reference case where no virtualization layer was used, then transferring the remote procedure call requests and data via a domain socket, then via a TCP socket via a loopback device, and using a remote TCP socket. As we can see, for matrix mul, n-body, and dpsim, we have a generally pretty low overhead due to the virtualization layer. Only for the hotspot application, we have a higher overhead, which is due to hotspot transferring the most data of all these applications. During this stage, we also identified two sources for overhead. First, the remote procedure calls increase the latency of function calls when we compare them to simple local function calls because of the additional overhead of setting up the network connection. And the second one is the data transfers between the RPC clients and hosts reduces the bandwidth compared to a simple transfer between the CUDA application and the GPU memory. So to measure these two sources for overhead in more detail, we also measured these overheads in micro benchmarks. So first, for the API overhead, we measured the execution time necessary for the two functions CUDA malloc and CUDA get device count. CUDA malloc just allocates memory, and as we can see, even without visualization, this function already performs quite a bit of work. So while the overhead is definitely there, it's comparatively not that high. But for the CUDA get device count function, which only returns a single number, almost all of the execution time when using the virtualization layer is overhead. Overall, we measure a maximum overhead of 36 microseconds due to the redirection. But we also conclude that the API functions are not called often enough to make this overhead that is shown here significant enough to be shown in overall execution times of application, as we have seen on the previous slide. The second source for overhead is reduced memory bandwidth when copying data from host memory to device memory. On the left side, we show the local data transfers where a GPU is used that is installed in the same system than where the CUDA application is launched. On the very left, we measure the reference bandwidth without virtualization layer. And if we compare that to the cases where we use a domain or TCP socket to transfer the memory over, we can see that the bandwidth is reduced quite a bit. Comparing that to the when we use the pinned memory API, we can use the shared memory segment, and we have a quite a bit lower overhead compared to the reference case, because we can save this extra copy operation that was necessary with the domain and TCP socket connections. For remote connections, the bandwidth is again comparable when using the IP over IP connection is comparable to using a local domain or TCP socket connection. Gigabit Ethernet is here only for comparison because it's very quickly at its bandwidth limitation, and so we didn't consider it further. And we also tried using IB verbs directly for the transfer of memory using the pinned memory API, which gives us quite a bit of performance boost compared to the TCP connection. However, we are still not able to fully utilize the full bandwidth of the InfiniBand connection. So to conclude my presentation, our virtualization layer is open source and so provides a basis for future research. It's fully transparent, so we don't need to modify application code at all. The performance overhead to application is generally generally small. We support Turing generation GPUs and CUDA 10.2 for these measurements. And we already implemented a few other APIs than just the runtime API. So we also support the driver API and some functions from higher level APIs such as QSolver and QSparse and so on. Yes, thank you for your attention. And if there are any questions, I'm happy to answer them.
All right, thank you for the talk. Let me see. So we have a question here on the Slack. It says, thank you for the interesting talk. How does this virtualization layer compare to the multi-instance GPU functionality in the Ampere architecture?
Yes, so that's pretty new. So when I started this work, this wasn't even announced yet, so I don't have too much detailed information, but even with the Ampere architectures, single root I/O virtualization, which they support, we still don't have full control of the interaction between applications and GPU devices. But we now can isolate multiple applications from each other that run concurrently on the GPU.
Okay, we got thank you in the Slack. So if there are no other questions, I have a few of my own. So how do you think the system works when you have a lot of short calls? Like, so if you have a program that calls I don't know, CUDA get last error, this happens a lot, right? When you do CUDA checks.
Sorry, I didn't get the last part. CUDA.
So sometimes there are CUDA checks in actually some of those samples.
Oh, yeah.
Those are macros that call CUDA get last error to see how the previous command ended up with and what was the error itself. Yeah. So how do you handle those cases? Is there a special case?
So actually, I thought that would make a big, would create a lot of overhead. But from these example applications, Matrix Mul actually performs like a few 10,000 of API requests, where the other applications only perform 70 in the order. And still Matrix Mul does not show a really high overhead. So the overhead of the remote procedure calls is not that significant overall, even when there are a lot of calls.
Okay, thank you. Maybe one final question we have maybe. So about slide 12, could you go there?
Yeah.
Yes. So you're talking about the bandwidth here. What is the size of the memory that you were transferring?
So I used the bandwidth test application also from the CUDA samples. I think I'm not entirely sure how large the memory was, but I tried it for different sizes, and the size didn't really have much influence above a certain point. So I think it's in the megabytes or something inside.
Okay, thank you. Any other questions on Slack? All right, so if not, let's, well, thank you for giving the talk. It's hard when you don't have applause or anything, so. And so I have a bit of time, but we could start earlier. So maybe Lena, you would want to share your screen?
Give me 1 second. Can you see now my first slide?
Yes.
Okay.
Great. You may begin when ready.
Okay, I can start to introduce myself. So I will talk about implementation and evaluation of CUDA Unified Memory Number. I'm a junior professor for computer engineering at the Fernuniversität in Hagen. And I'm very happy that it's a virtual conference right now, because usually I could not participate because I'm a mother of a 1-year-old. So I'm very happy that it's a virtual conference and I can talk, because I could never make it to Poland in my current situation. And today I want to talk about this work, which is basically the work of my student, needed implementation, and I only did something in the evaluation. Yeah, let's start with the motivation. Why I'm looking at this kind of work. So I had a few work about number and CUDA. The point is that most HPC and parallel applications are written in C++ or Fortran. But the problem is that a lot of people today don't learn these languages, especially my students. They want to learn parallel programming, but have no idea about C or C++ or Fortran. And it's very hard to teach them parallel programming, because you first have to teach them C or C++, which takes a lot of time. So I started to look in other ways. And I have to say, not only data science, of course, it's very popular, but also in physics or in biology and engineering, a lot of people today use Python. The reason is that Python uses a lot of precompiled libraries, which are basically written in C++, like in SciPy or NumPy, or which are very easy to use for these people. And these are kind of okay for performance. But if you really start to write applications in Python, it's much slower than bare metal C, because of course Python is an interpreted language, and you have always this object handling, which increases the memory footprint. Of course, NumPy is somewhere around it, where you use really memory. But still, if you use normal Python, you get a lot of performance penalties, which is not really made for high performance computing. So if you don't use classic libraries, and if you really want to write computational code in Python, it's always kind of slow. And that's why I'm looking in ways to use Python for parallel programming and speed up applications, but not only using in libraries, but really using and writing algorithms in this language, and especially computational intensive applications. And by doing this, I ended up in Number. Number is a package for Python, which allows you to, well, speed up compute intensive application parts. And it's doing it by being a just-in-time compiler. So basically, it's very easy. You just, well, it works together with NumPy, but you just have to mark some functions you write in really Python code. So it's not a wrapper like Cython or CUDA. You really have some functions and you just mark it. And then they are just in time compiled when the script is running. And one nice thing for me is, because I'm also looking into GPU computing, is that it has support for CUDA and for NVIDIA GPUs. And you can do some GPU programming, CUDA programming in a really Python-like style. So on the left side, I've got an example how this works. So this is the simple matrix multiplication written in Number for GPUs. And people who are a little bit familiar with GPU computing in Python will recognize a lot of things. You can use shared memory, for example. You can access like local variables like thread IDs and so on. The nice thing, what you can do is you can use the Python indexing for accessing large 2- or 3-dimensional arrays, which makes it very easy. And well, if you run an application and call this kernel, it just compiled, and then it's one of the NVIDIA GPUs. In my previous work, I just want to mention it here, I looked in how good is the performance of this, and I looked in several kernels, and these are just the results for the Gloverleaf benchmark. So I looked into a lot of computational intensive kernels, and as you can see, so this is only the computation time of the kernels. I'm not looking at any kind of in-between overhead and so on. This is really the pure GPU time. And what you can see here is that the performance of Number, so that's the total runtime, so smaller is better, that CUDA, bare metal C CUDA is always better than Number. We did some optimizations inside Number to get a little bit better performance, but basically bare metal CUDA always stays faster. So if you really want to get good performance, you still have to go back to C, but to get some experience, to try yourself out, this Python way is always a nice way because it's just easier to learn. In this remaining overhead, why number is slower than CUDA. We're still not completely behind it, but basically it's based on the LLVM or NVMM because this is how it uses. So it uses this in the background, and if you use LLVM with CUDA, it's always a little bit slower. So you get not the full performance, but it's still satisfactory. So in this previous work, I basically look at the computation time, and in this work, we more looked into the data transfer time. So how long does it take to transfer my data to the GPU? And in number, there are 3 ways how you can do this. The first way is implicit. So if you allocate a NumPy array and call a CUDA kernel, so in the second line in this example here, you can see how you allocate memory, you can start a kernel in number. And if you do that implicitly with normal NumPy arrays, the data are just transferred in the background. So number just copies the data to the GPU before the kernel starts and copy it back when the kernel is completed. You can also do explicit data transfer, like you know it from normal CUDA programs in C. So you can allocate CUDA device arrays and then do an explicit data copy. This is more or less a normal way. You can also do this with pinned memory. So in this example, I just use a normal NumPy array, but also number supports pinned memory arrays. But I didn't do it here. In the benchmarks, I did it just to show the example. And there's also one thing which is called a smart array. In this case, for smart arrays, the data transfer is managed in number. So it's kind of a way to not copy always all data back and forth, because, for example, if you don't need the results, you don't have to copy it back. And if you just write to an array, you don't have to copy it to the GPU before. But basically, the smart arrays are for some reason decrypted in your number versions. So we still use them to look how well they perform. But if you use a newer number version, they're no longer there. So now CUDA in C has this thing which is called unified memory. And if you use virtual memory, you have so you don't have to care and see about all this data transfer. You have one single virtual address space, which is shared between the CPU and all GPUs on one host. In newer versions, basically the memory is accessible with the same virtual address from all devices. On all the GPU systems, this is basically done by copying data forth and back in a smarter way. On newer GPUs, you have some hardware support for this, like demand paging, where basically the pages are moved when they're accessed for the first time. In our test system, which is a Power 9 with a Pascal GPU, this is basically the case. And even there, you also have more sufficient support, because you basically have one physical address space, so you basically can access all memories from all devices without transferring them. Yeah, but this basically is not supported in number. So the basic idea of this work is to get it working on numbers that I can use the idea of unified memory inside my applications. One reason why we did this was the support for system-wide atomic operations. So if I have a unified virtual address space and I have support for global atomics, I can do work distribution, a dynamic work distribution between the CPU, the GPU, and other GPUs on the same device, which is very interesting. One important point we always have to keep in mind, if you use unified memory, it simplifies programming a lot, because you don't have to take care about data transfer. It's all done in the background or by the hardware. But basically, in a lot of previous work has shown that the performance of using unified memory is worse than using explicit transfers, because if you really know what you do and what data you want to transfer, you will always be better. So it's more like using Python, a simplification of programming, but not a performance thing to use unified memory. Yeah, the implementation in number. The first idea we had was to basically replace all malloc applications in Python with CUDA malloc manage, at least on hardware which supports this, because you can use it for host allocations in the same way. The big advantage is that you don't have to change applications. You can just use your all applications and in the background just manage memory is used. And actually we like this solution, because if you have a machine which supports it, it's a very clean solution because you just see your machine as one big machine with one big memory area. The problem is that it still requires expensive bookkeeping because we can change in Python the allocation function, but not at the beginning. So the first few allocations would still use the old malloc, and later allocations would use the new one, and then you have to keep book which memory area is allocated with which function, otherwise we get segmentation faults. The other problem is, of course, that it's not compatible with old architectures because old architectures do not support unified memory and especially not the hardware support. And the last reason is that CUDA malloc manage is slower than malloc, so much slower. And this would affect all applications using Python on your PC, and they would all get slower just to get some benefits on GPU applications. So that's why we decided against it. Instead, we created a managed array class in Number, which is the subclass of NumPy arrays. You don't need special bookkeeping, only the bookkeeping which is already part of NumPy arrays, so that you use the allocation functions once you give your memory free. It only affects GPU programs. The only problem is that you have to do some changes in the applications, so you have to replace the allocation calls with this managed array class. But that's why we used it. So we defined a new array class, which is called managed arrays. It's a derived class of NumPy in arrays, so you can basically use it in the application like normal NumPy arrays, and basically all NumPy functions could use it. Basically, it was very simple to implement it. We only had to replace alloc and the allocation calls in the class, and most other functions could be inherited. The only thing we have to take care for is to mark it at GPU memory in Number, because otherwise Number would start to copy data explicit around once an application is started. And in the corner in the square below, you see some examples like Number CUDA managed array. You allocate an array which is allocated on managed memory. You have a shape, so people are familiar with Python, NumPy will recognize this, so it's very simple. You can also use basically all functions you're more or less used to Python to allocate memory in allocate an array in managed memory. Another important point I talked before are global atomic operations. So local atomic operations are supported in Number for CUDA, which allows you synchronization between blocks on the same GPU. But new architectures in GPU architectures allow global atomic operations, which allow synchronization between multiple GPUs, and also synchronization between host and GPU. So you have one atomic operation which is current on host and GPU. But this required some unified memory. And one important point of implementing this was also implement this atomic operation. So in the LLVM, there's no direct support because these NVMM, which is the CUDA LLVM library, is closed source and you cannot really look into it in a legal way. So we use inline assembly operations in the code to implement these atomic operations. We also had to implement atomic operations on the CPU because they're currently not part of Number, so we had to do it on both sides. And this was very simple because we have to just internally add functions which add this atomic function for add and compare and add inside the intermediate code. And now we can see examples on the GPU. You just have to call Number CUDA atomic system add, which is a fetch and add operation. On the CPU, you have to do the same thing. So you have an array and then you have an index in the array where you want to access this, and this would be an atomic operation. The first one would be used on the GPU and the second one would be used on the CPU, and you can use this atomic operation on both devices and on all GPUs. Now we come to the performance evaluation. We have first 3 synthetic benchmarks, but I will only show the results of 2 of them because the last one is very similar to the second one. And yeah, it would get very boring. So the data transfer full is basically a very synthetic benchmark. All data are transferred before and after the kernel call. and you do a computation. So you copy all data to the GPU, you do simple computation and copy the data back. The second is you have basically two arrays. You copy the input data to the GPU and only copy the output back if you use explicit copies. One point to note is that we measure timing and not bandwidth, because if you use unified memory, it's kind of hard to measure bandwidth because the data are copied while the application in the kernel is running. And also, so we included data transfer to the GPU, running of the kernel, data transfer back, and a simple result checking on the CPU in the complete runtime. We included this CPU time because if you use unified memory and you don't do anything with the memory afterwards, the data will just stay on the GPU. So we also added some CPU computation on this array to guarantee that the data are copied back and are still accessed from the CPU. So the runtime always includes transfer to the GPU kernel, data transfer back, and CPU computation. So look at the first benchmark, the full transfer. So we have one array which is copied to the GPU, do some computation, copy back, and so on. So we see, and lower is better because we have latency. So we first see that, of course, explicit copies with pinned and non-pinned memory. So in this case, we look at both are always best for small arrays and for larger arrays. Managed memory for smaller arrays is kind of in the same area. So it's, of course, worse than explicit data transfer, but at least for small arrays, it's better than implicit copies or also like smart arrays. For larger, if you have to transfer more data, but also do some more computation, this changes a little bit. Of course, explicit data transfer is still better, but now managed memory gets much worse than smart copies, explicit copies, and implicit copies. So implicit copies in this case are not basically because you always copy all data. So in this case, the implicit copies is also doing the best case because always all data are copied. So this is kind of expected, and this matches more or less the results from unified memory. The more interesting part is why are we better for smaller arrays? Because this is nothing you expect, because if you use managed arrays, you always expect worse performance, at least if you always copy all data. If you look at the partial transfer, so in this case, not always all data have to be transferred. For smaller arrays, it more looks the same. The only thing we see now is that the implicit copy case gets a little bit worse. And the reason is that we have always extra data transfers, because if you're using implicit transfers, always all data are copied, but basically we don't need this. And this effect gets stronger for larger arrays. And now the implicit copies are much worse than our managed copies, which is nice. But of course, managed arrays are still worse than smart and explicit copies for larger arrays. We also compared with a similar benchmark in C. So I don't want to make the C and number comparison here. I just want to see the relative changes. And if you look at C, you see that there's a huge difference between managed and explicit copies and pinned memories, which is not so strong for number. And so I really like to understand what is the reason for this. Why we have like a better performance for managed memory for small arrays? In this case, for small arrays and for this full benchmark where I copy all data. So why is my managed memory here better than using implicit or smart copies, where I basically do the same for this benchmark like for pinned for the explicit copied arrays. So what I did then, I looked at a trace. So I looked on when is what function called. And on the bottom, you can see the function called and what is called in C. So a C pinned explicit, you see you first have an event. I used events to measure the time. You have a CUDA copy, of course, because you copy the data. Then you launch a kernel, you copy the data back, and then you wait for synchronization. And all those functions are very, very close together. In the last line, you see for C unified memory, this is also what you would expect. You start with an event, you launch the kernel because you don't have to do explicit data transfers, but now the synchronization takes much longer time, which means that the kernel needs much more time because the kernel, while the kernel is running, the data are transferred and you have a lot of page misses on the GPU, and that's why the kernel time goes up. So this is for unified memory and this is for C, and this is why unified memory is always slower, because the kernel gets so much slower because you have a lot of page faults and the data are transferred while the kernel is running. So, and what you now see for the Python applications is that you have a lot of, I say, white space between the function calls. So there is not a lot of stuff happening here, what you can see. So in C and Python, the code looked exactly the same, but we have this long distances and this long white spaces between my actual function calls. And this is here the Python overhead. So in Python, of course, this thing is, you call the C functions. Once you're in the function, you get the full benefits of C and compile code. But in between these functions you always have the Python overhead. And this is why you get this very, very huge white spaces where you can see nothing happening in CUDA on the application when you do a tracing, because here everything in Python is happening and a lot of overhead. And basically this is the reason why unified memory is better for, let's say, small data transfer and small kernels, because you reduce your number of function calls. So because you have less function calls, the Python overhead gets less because you don't have to do malloc calls, you don't have to be copy calls, you just call my event call, you launch your kernel, you synchronize your kernel, and then you finish it. So you don't have so much overhead from calling more functions. And for Python, this pays off if you have a lot of small kernels and small data transfers, because you reduce the number of function calls, you reduce the number of overhead in Python, and by this you reduce the runtime of the applications. The other thing we looked at are the atomic operations. And for this, we look at the tri-benchmark suite, which is a collection of benchmarks which distribute works between CPUs and GPUs. Of course, these benchmarks are all written in C and C++. So we had to translate them to Python and Number, and we use the RCD benchmark, and we implemented 2 versions of it in Python. The first version uses discrete memory, so explicit data transfers and static workload distribution. So the work is distributed between GPUs and CPUs by just partitioning the input space. So the first version distributes the data by using static workload distribution. And the second one, which uses unified memory, uses a dynamic workload distribution by using atomic operations. So basically you have an fetch and add operation where you get which are the new data, and we implemented both versions of it and run it on our system. And here are the results. So the first result is only GPU. So first you can see, which was kind of a little bit disappointing because of our GPUs, which are very fast, basically only using the GPU and not using the CPU at all was always the fastest solution. And this is the first one where you only use the GPU. And here you can see that just by using unified memory, you get a lot of benefits for this application. And the reason is that the runtime of the kernel is slow and you don't have to transfer that much data. So the benefits we saw for the micro benchmarks here fully pay off. And that's why you see a huge performance improvement for the unified memory use case instead of the static distribution, which uses explicit data transfers. So if we know to start to distribute our work between GPUs and CPU, as in we only used one GPU and the CPUs, we first see a massive increase in runtime. And basically, again, here the problem is the overhead, because we use, of course, Number and the CPU part of Number to do this code, but this also has a lot of overhead, and the CPU is much slower. So we see this massive increase of runtime. And another problem is the global interpreter lock of Python. So if you use tools like Number and so on, you can do some parallelization. But basically, Python is not able to parallelize code because of the global interpreter lock. So if you use Python threads, your code is serialized internally. And that's why our runtime goes up if you use more CPUs. But basically, at least we can see that if we don't use too many CPUs, we see some benefits from this unified and this dynamic work distribution. So the conclusion is, like I said before, the performance of unified memory is in most cases always worse than explicit data transfer. But as I said, this is also true for C and C++ and wherever you use it. But if we use it in Number and in Python, we can at least benefit in some cases because we have less function calls. And this leads to less interpreter overhead. So you always have to find a sweet spot between how much is your overhead of calling functions and the overhead of calling the Python functions. The nice thing are these atomic operations, which allows this work distribution with CPUs and GPUs. This can lead to a better performance, but well, the problem is here, where we're also working at the moment on, is this global interpreter problem. So you want to find a better way to start multiple threads together with Number to get a better work distribution between CPUs and GPUs. The next thing we want to look at are other hardwares, like embedded hardware, like for example, the Jetson Nano. So we already looked at it, and here the results for using unified memory are much more promising, because basically here we have only one memory area, which is shared by GPU and CPU, and here we get a lot of performance benefits by using unified memory. The only problem, and that's why the results are not in the paper, was the missing space, and the Jetson Nano is not supporting global atomic operations. And we're also working in combinations of techniques with MPI for Python. So basically, I like to really make use of Python for parallelization, and that's why I'm looking into this. And we are looking into improvements between CPU and GPU synchronization. And this was basically my talk, and I'm open for all kinds of questions.
Thank you for this very interesting talk. We are now open for questions on the Slack channel. Seems that there is a question being typed. Okay, so there are two questions here from Maria. First question is, are the Number optimizations automatic in slide 4?
Well, yes. So basically, it's my optimizations are it's a patch for Number. I'm basically working in to make it like widely used. But once you have used it, it's basically using signed integers instead of unsigned integers for indexing. And this brings most of the performance improvement. So it's, if you apply my patch, it's automatic.
Mm-hmm. Thank you. So for the second question there is, have you taken a look at the aggregate overhead of Number in a full stack application?
Well, I did it in my previous paper in this for the Cloverleaf benchmark, and you can see that the overhead in Python is the biggest problem right now. So what I see there is that if the switching between calling CUDA kernels and the Python overhead is too large, so in this case, if you have a smaller problem size and the GPU time is low, the overhead gets more expensive. If the GPUs are running most of the time, it's gets better. But the Python overhead in between calls to the GPU are the biggest performance problem. It's much bigger than the performance problem we have for the pure computational kernels. So yeah, that's the biggest problem.
There are more questions coming up. So first of all, you're thanked for the answers. Okay, so in the meantime, while that question is being typed, then I will ask a question of my own. So what was your experience with, well, copying different regions of data or subregions of the same arrays with unified memory? So did it normally fit page sizes? Did you have any excessive copies that you've noticed that were happening?
Well, this is basically a question of unified memory, and the kernel will behave more or less the same. I don't look into this work explicitly into this, but in other work. So if you only access partially kernel, this is actually something I should look at. I think it could be better in some cases. So if you only look at pieces, but probably this is also one thing I should look more into detail for this CHI benchmark, because here I only access part of the input data if I parallelize the code between CPU and GPU and don't copy the full array. But I have not looked into it in this work in detail.
Thank you. Are there any other questions on the Slack channel? I saw someone type and then that disappeared, so maybe there is a question. All right, so thanks again.
Thanks for listening.
We're still ahead of schedule. Maybe we should wait for a minute before starting the next talk, I guess. So meantime, we can set up. So, Yuxiang, you want to start sharing the screen?
Okay. Yeah. It works?
Yes, it works.
Okay. So I start now or just later?
Let's wait maybe half a minute or so, I think.
Okay.
Yes. Okay, so you may start.
Okay, thanks. So hi everyone, my name is Yuxiang Magtai, and I will present the preparing Ginkgo for AMD GPUs and a testimonial on porting CUDA code to heap. And this work is also done by Terry, Tobias, and Harwick. So let's start. So in the past, the NVIDIA GPU dominates in the super GPU market. But in the following years, we can see there are some leading supercomputer will equivalent with the AMD GPU like Frontier system in Oak Ridge, or maybe in next year, or in 2023 like El Capitan. So for now, we can say AMD trying to get back to the supercomputer market. And also AMD give a very useful language called heap, which is very similar to CUDA programming. And it also provides the similar interface with the CUBus and CUSBus and some functionality with CUDA. So they also provide, you can compile the heap on the AMD GPU and also on the NVIDIA GPU. So they want to try to attract the people with familiar with CUDA and to come to the AMD GPU, and also want to reduce the learning gap with from the CUDA to AMD. So here we will show our experience to port the Ginkgo from CUDA to heap. And so we have some questions on how we prepare our Ginkgo library for cross-platform portability, and also how does the heap affect the performance on the NVIDIA GPU. So Ginkgo is one open source sparse linear algebra library, and it's on the many cores architecture. So we introduce our library design. So we have one core structure. It will introduce the library interface and also some algorithm implementation. So I would say it's most likely the pseudocode like with different solver, like maybe some Wikipedia shows and just say, or like CG, we need some dots product and some SPMV or some norm calculation, you just disarm, but the detailed implementation will in a different kernel. So originally we split the kernel to reference, OpenMP, and CUDA. So for reference, we will write a simple code and it will run in sequentially. And it's target to get we can make sure the algorithm is correct or not. And we also use Google test to check each kernel is run correctly. And we also follow the OpenMP. The OpenMP is mainly for the CPU, mainly core CPU. And also for CUDA, we write a CUDA for NVIDIA GPU. So we also, but because we also want to check the implementation is correct, but so we compare the results from CUDA and reference and also OpenMP with reference to make sure each kernel is performed identically. And not identically is some correctly, yeah. So when we call the code, we use runtime polymorphism to you give some executor with reference or OpenMP or CUDA, and the runtime will choose the correct kernel to run it. So after that, we want to support heap. So give the similar idea, we just as one heap structure similar with the CUDA. So it will implement the SPMV and solver or precondition some kernels here. So we also use Google test to here. So before detail, I just want to show how we use the Ginkgo in from the user side. So it's just a simple cases for from CG with the Jacobi preconditioner. So we can just create a which create one GPU executor on CUDA and with the host executor and read the matrix to store in the GPU and create a solver and give some criteria. And we just generate and solve it, that's all. So from the user side, if we just want to change the CUDA to heap or want to use OpenMP or some just want to check our algorithm is correct, use the reference executor, we just need to change one line from CUDA to heap or to OpenMP to other executor. So it's very easy to change architecture with different platform. So going back to here. So for CUDA and heap is GPU give with some similar idea from the SIMD. So we can see we can compare the CUDA language and heap language and not. So if we copy the almost everything from CUDA to heap, if we need to debug or change or fix anything, we need to handle the code in two places. It always gives annoying text also will give some potential issue here because maybe we only change one place but forget to change another place. So we can see the CUDA and heap language here. It's just a simple code here. So we can see the kernel implementation is almost is identical in CUDA and heap, and also but in the kernel launch the CUDA and heap use the different kernel launch syntax. So the idea is right now we just move the identical path to one file, and for the CUDA and heap structure, we just keep the different path. So we just create a common folder. It will store the identical kernels from CUDA and heap, and in CUDA and heap structure, you will leave some parameter configuration or some different runtime syntax. So because this design, because we recognize the CUDA and heap will running on the different architecture, so some tuning parameter will be different. And also the major difference from NVIDIA GPU and AMD GPU is CUDA use the 32 as the warp size, but the AMD GPU use 16.4 as the wavefront. So it's usually change the performance between these parameters. And moreover is the CUDA supports the dynamic parallelization, and it's not fully supported from AMD. So we want to keep the most technology from CUDA side, so we still keep separate from CUDA and heap. So not always code heap on the NVIDIA GPU here. So looks like heap everything is fine, but unfortunately the heap do not only support green and black white cooperative group, but not sub-white cooperative group. So cooperative group is a nice virtualization from CUDA 9. So it can give one module to represent one group of several threads, and it will give you some benefit to debug or to make sure you make all threads in one group involve one kernel. But heap do not support website, but we use a lot. So in official heap support, we need to call Lankes shuffle or some WAF stuff. But in Ginkgo CUDA's code, we usually just use the cooperative group code. So we cannot directly convert the codes from heap to CUDA. So we implement the Ginkgo heap cooperative group interface to support our needs functionality in cooperative group from heap. So after that, it will be identical again. So we can see this part is the identical kernel to move to the common kernel to reduce the code duplication. So this is just some simple implementation. So we this size will be the WAP size here will be 8. So this one is the second WAP, and we give the sub WAP size equals 2, and we can easily compute the rank. And the shuffle function will need rank and size. So like shuffle XOR or shuffle up or shuffle down. And moreover, we need the length offset. So it's the more complicated, more long computation about this one. And also for the max. And we can use we need this additional information because like both function needs the length offset and mask, like the any match or balance. So after that, we implement all we need in the Ginkgo library, so we can use this as CUDA implementation. So of course, we need to check our implementation is not do not affect the performance a lot. So we write a simple reduction kernel to make sure it's not too different between the legacy code or the cooperative code. So the solely box will be the legacy code. So it will be like here, the shelf code XOR, and the cooperative like here. Okay. And so here we compare on V100. The left part will be on the compile be from the CUDA structure. So we can see it's almost similar, and some copy just a little affected, but just some machine noise, but looks like very similar. And our implementation is in heap. So heap also can run on the V100 because AMD design. So we can see the cooperative group also. Our implementation is not affect the performance, and also here. And we also run the heap kernel on the AMD GPU Radio 7. So we can see also they give the similar performance with the legacy code or cooperative code. So we can say our implementation is do not affect the performance, so we can safely to use it. So of course we can also make sure our implementation is for the reduction is correct. So the simple reduction will depend on log sub-WAP size. So we can get the ratio between the size equals 4 and size equals 32. So the theoretical ratio should be 1/3, and we get the average will be 0.36. And also for here, the full warp size in AMD is 64, so it's equals 0.4 here, and we got the average is 0.394. It's very close to theoretical ratio. Yeah. So after that, we give our analysis of Ginkgo code. So original we have CUDA and other stuff, and we add some new code here. And after that, we move the shell kernel to the common folder, and some parameter and some specific implementation in CUDA here, and also the new code almost for heap, including our implementation for cooperative group. So we can see the CUDA and heap almost have same amounts in the code, and the common will be here. So CUDA plus common will be the CUDA structure in after comparing, and heap plus common will be the heap part. Yeah, so the common will be the kernel, and some hardware specific parameter will be set in the CUDA or heap structure. So this one is just the Ginkgo protein workflow summary. So because we need to handle NVIDIA GPU and AMD GPU separately, so we need to use variable to represent the hardware specific parameter, like warp size or wavefront, and or some more tuning parameter. And we move all shell code into one common file to avoid the code duplication. And after that, we can set the parameter before we include common file, and it can be different from CUDA and heap. So after that, we can include it, and we can use the script to convert the CUDA code to heap code. But it's not only heap file. Heap file is a very good tool from AMD. It can convert almost every CUDA code to heap code. But we need some other stuff or fix for Ginkgo. For example, we already implement the cooperative group, so it will handle it, and or some CUDA namespace to heaps namespace, and also some fix from here. So we call, in CUDA, we call CUDA namespace kernel here, but after heap file is just converted to namespace heap launch kernel here, but it will give error message. So we need to move the namespace next to the kernel name. So we also handle it automatically from the script. And also after that, we get heap file, so we can modify the heap file, the parameter to support different architecture. So after that, for now, Ginkgo already supports heap fully. So because heap also can run on an NVIDIA GPU, so we also curious about does heap affect the performance a lot or not. So we trying to run it on the NVIDIA V100 with heap and with heap language and the CUDA language. So we expect the CUDA will be a little faster because heap will add one additional wrapper on the CUDA. So it's the CLP SPME here. So except for some outlier, in general, it performs our expect. But the outlier is maybe some machine noise or some compile different, because we also look at the PDX code is we see a little different from CUDA compile from CUDA structure and from the heap structure. So maybe it will introduced by the difference or some machine noise here. And we also analyze the least outlier. So in each one, it should be very close. So it should be some more compile side, but not the machine noise here. Yeah. So we also run another stuff from the GIN code against the CUDA and heap code on the V100 is from CLP, our implementation, and the sparse library CSR, and also our COO. Our CO will use a lot of atomic edge, so we can also make sure the atomic edge will not the big issue in the between the heap and CUDA, and also the contributor gradient solver. So in general, it's as our expect, the CUDA has more, it's a little faster, but usually just smaller than 5%. So in general, the heap is do not introduce a lot of overhead about on the NVIDIA GPU. So we also run in on the performance analysis with different architecture. So before that, I introduced we use the performance profile on the analysis. So this is just a quick example. So it's the 4 problem with the 3 implementation. So give this table, we can get the performance profile. So in the first, we need to get the ratio between the time and the fastest one. So here, and we can compute the maximum slowdown factor over the fastest one. So when slowdown factor equals 1, we can guess which implementation is fastest. So slowdown factor equals 1 will be A has the 3 of 4, so it's 75% here. And B implementation will be only 1 of 4. So it's 25%. And C here. So we can increase the slowdown factor to 1.1, 1.2, and 1.3 to count how many problems we alone in the allowable slowdown factor. So like in 1.2, so we can count how many problems under the 1.2 here. So A still be 75%, and B will be 100% because everything is under 1.2, and C only have 1.16. So give this the performance profile, we can get more information than one picture. So in the one here, so we can know the A implementation is the best one in all of our problem. But if we would like to get more generalized implementation, we maybe need to choose B, because if we choose B in our problem, we only get more 1.2 slowdown, but otherwise for others maybe have what, like for A, you get 1.35 slowdown, and C is more slow. So in here we can see the best one or the generalized one. So we also run its performance profile on NVIDIA V100 with different SPMV. We have COO, CSR, hybrid, and we compare the CUDA sparse implementation. So in here we can see our CSI is the best one in, we take the all matrix from sparse, which contain the non-zero large than 10,000. And although our CSI is the fastest one, but after that, we can see the hybrid will be the most generalized for in most problem. So if you choose hybrid, you only get 1.5 or 1.6 slowdown factor, but you solve every problem here. So also we analysis on the AMD GPU. So for the Radio 7, we also compare the SPMV. So it gives similar performance profiling. So our CSI still be the best one, but it's more cost to HISPA CSR. But our hybrid will still be the generalized one. So maybe if you want to solve all problem, you choose hybrid, you need to accept 1.9 slowdown factor here. So we also compare our Ginkgo Krylov solver. So the bright line is the theoretic, practical bandwidth here. We use the bubble stream to test it, and also we compute our bandwidth for by CG straight or CG or GMRS. So in NVIDIA V100, we are close to the practical bandwidth here. Like we can get like 85% to 90% here, or even like very close to practical one. But in Radio 7, we have a little far away from the practical bandwidth, so it's a little slow down here. So it's maybe because we use a lot of dot product in our kernel, and the dot product in the benchmark is introduced as more slow than CUDA V100. It's maybe because Radio 7 is give lower double performance, or because the implementation, we do not dig into the AMD implementation. Yeah, so it's summary. So AMD gives a very good tool and language HIP, and it's very similar to NVIDIA CUDA. So it's very, the learning gate from CUDA to HIP were very small. So you can just use HIP file to convert CUDA from CUDA to HIP. And also HIP can alone compile HIP code for NVIDIA GPU. So depends on usage, you can just keep your HIP kernel alone, and you don't need any CUDA structure here. But in our case, we want to keep the latest support for CUDA, so we still separate CUDA and HIP in Ginkgo. So in our performance profile, we can see AMD and NVIDIA GPU give comparable results, because in the sparse linear algebra, they usually is memory bound algorithm, so it's not affected from some double performance. It only depends on the bandwidth. So for now, Ginkgo it already supports all functionality in Ginkgo for NVIDIA or AMD. So we have 5 format SPMV, and we have a lot of Krylov solver, and also for IDEA and multi-grid is work in progress. And also we have some preconditioner, ESI or adaptive block Jacobi, and some vectorization IRU or PyIRUT. And for now, Ginkgo is also support CUDA 11 and Pi. So we trying to keep our cross-platform capability between the CUDA and HIP, and give the good performance between on the different platform. Okay, thank you. So any comments or question?
Thank you for the very interesting talk. See, I think that it's very valuable to have some experience with AMD GPUs as well, and with HIP now really up and coming, to see what the difficulties are. So I give the stage now to questions from the Slack channel. In the meantime, maybe I'll ask a question by the time the questions are typed. So basically, what you said in the middle of the presentation is that the cooperative group implementation in HIP is lacking some of the elements that you need.
Yeah.
Now, have you considered with your newly implemented parts to make pull requests to the HIP GitHub repo? I think they're open for these things.
Yeah, we are considering, but we still discuss it. And in the beginning, we already see there are someone implement it for HIP, but we do not entirely sure why for now they only keep the group and block implementation, but it might be possible. Yeah.
Okay, so now a question from the Slack channel. So it says, thank you for your talk. What would you say was the biggest lesson you learned in the porting?
I would say in the porting, because the code NVIDIA and AMD design is coming from the similar idea is SIMD structure. So the kernel implementation usually is similar. So we don't want to introduce too much code duplication. So in the first one, we just we use the separate structure to keep the two same code. It gives a lot of annoying to maintain this one. So after that we just keep the same code in another folder to reduce some annoying works between CUDA and HIP.
Thank you. So another question is, how does this work relate to SYCL, SYCL?
So SYCL is, okay, so I'm not sure. So the SYCL, we will like Intel one API. So for now we are working on this one, and we also discuss with Intel people and we also trying to support the Intel GPU in the future. But for SYCL, I think we need more works for SYCL or the Intel One API because the language is more far from the CUDA or HIP, so it's not likely we can just use the same identical code kernel here. But we will try to see how to use it. But in the future, we should support the Intel GPU.
All right, thank you. Any more questions from the Slack channel?
But of course, we should try to avoid the code duplication also in the SYCL. So let's see in the future. Yeah.
So I have two more, let's say, lower level questions. So one question is about, you said you were using get the current lane and get those offsets from the threads. So have you looked at the device functions in HIP? Like I think they have some lane mask and other functions built in. And I think those were similar to the ones that CUDA provides.
Yeah, so there's some device API for it, I guess, but we just write it our own because it's very simple computation and looks like it do not give a lot of overhead, so we do not look into more detail. Yeah.
And last question from me, I know, so if you go to slide 15 in your presentation.
Okay, maybe I can share my screen again.
Yes.
Here?
Yes, on the right-hand side, you have a legacy implementation.
Yeah.
So what is that? What is the language that you were using as a legacy?
Oh, the legacy one just called the API, the original API. So it's almost like here, like just directly call the shuffle XR, but you need to compute the bit mask or not the size, what size here. So it's the right one will be the legacy parts, and the left part will just call the cooperative group kernels. So in the shuffle XOR, you just need size. It's much simple cases, but in more complex case, you need like length offset or max for the match or for annual or like vol function. So it's the legacy part here. Yeah.
All right. Thank you. So this concludes the session. I think now comes in the scheduled lunch break. That ends at 1:15. Okay. So thank you for all of your talks.
Thank you.
See you at 1:15.